Hello there, and welcome to Simple Sleepy Science. Tonight, the Airbus A330 will guide our quiet learning. It is a large, familiar shape, built by Airbus, with two engines resting beneath its gently swept wings. Inside that wide body, two aisles pass through a cabin whose arrangement changes from one airline to another. A330s work across medium and long journeys, but tonight we can travel without needing to go anywhere. We will simply notice the parts that usually blur into the background, beginning with the softly rounded nose. Above it, the cockpit windows form a dark band where two pilots will later watch the route unfold. Farther back, a broad turbofan inlet waits in silence, its many blades motionless before the next departure. The second engine mirrors the first, giving the passenger A330 its balanced twin-engine outline. Each wing reaches outward and slightly backward, carrying control surfaces, structural strength, and much of the aircraft's fuel. At the tip of a classic A330, a small vertical fence gives the long wing a neat ending. Below the wing, four wheels on each main landing gear unit hold the aircraft quietly against the concrete. The tall tail remains visible from across the airport, even when much of the fuselage hides behind the terminal. From indoors, it can seem less like a machine awaiting work, and more like a room waiting to open. A jet bridge meets the forward door, making a short enclosed path between the terminal and the aircraft. Across that threshold, the scale changes from a wide airport view to handles, panels, fabric, and soft light. The two aisles run nearly parallel, dividing the broad cabin into seat groups chosen by the operating airline. A common economy pattern is 2 seats, then 4, then 2, making 8 places across the cabin. Overhead bins follow the ceiling's curve, holding the small belongings that passengers bring into this temporary room. As the lighting dims, edges become gentler, colours recede, and the long interior begins to feel more settled. Beside a window, the wing becomes the main landmark, steady for now against the scattered lights outside. Later, we will visit Toulouse, where large sections come together during final assembly of passenger A330s. We will follow air through a turbofan and see how one continuous flow becomes thrust, electricity, and conditioned air. We will enter the darkened flight deck, where displays gather the route and aircraft systems into an ordered view. We will trace a long ocean route and the careful layers of planning that surround every distant line. We will also see how this same family carries containers, freight, fuel, medical equipment, and unusually large aircraft sections. All the while, real A330s continue their overnight routines, arriving, unloading, resting briefly, and leaving again. By dawn, we will return to this quiet stand, knowing a little more than we did in the dark. The year is 1987, and the familiar aircraft before us exists mainly as drawings, calculations, and choices. Airbus already had an established wide-body fuselage cross-section, and the new program could build from that useful foundation. Rather than beginning with an empty page, engineers carried forward a broad cabin shape that airlines and factories understood. That continuity mattered because a 2-aisle cabin was already a practical way to arrange passengers, baggage, and service. The quieter story of the A330 is therefore a story of adaptation, not a single sudden invention. Airlines wanted wide-body capacity on routes that varied greatly in length, demand, and the airports at either end. A useful design needed room above the floor for people, and below it, for baggage and revenue cargo. A long centerline appeared first, followed by the rounded nose, cylindrical cabin, tail, wing, and landing gear. For the A330, two large engines would provide the defining arrangement beneath that common wide-body shape. Its intended work sat across medium to long routes where a broad cabin could be valuable without using four engines. The circular fuselage had to serve two floors at once, with travellers above and rectangular cargo spaces below. Some planned journeys would last only a few hours, linking busy cities with repeated wide-body service. Others would stretch across continents and oceans, asking the same basic airframe to remain useful for much longer. Airbus studied the twin-engine A330 beside a closely related four-engine aircraft called the A340. On June 5, 1987, Airbus formally launched the combined A330 and A340 program. The pair were developed in parallel, which explains why their outlines can look so closely related from a distance. Their fuselages shared a closely related design, preserving the same broad cross-section through much of each aircraft. Their original wings also grew from a common design basis, even though the engines beneath them would differ. The easiest distinction is the count: 2 engines for the A330 and 4 for the original A340. Inside, much of the broad cabin geometry remained familiar, while the aircraft were prepared for different operating roles. Parallel development let Airbus shape 2 answers around many common structures, tools, systems, and production methods. As the drawings matured, the twin-engine member gained the identity we now recognize as the A330. In Toulouse, ideas on paper became immense pieces of metal and composite material, waiting in careful alignment. Separate fuselage sections were brought together until the long cabin became one continuous pressure-bearing structure. The wings met the center section, creating the strong structural crossing that would later carry lift and fuel. The vertical tail rose into place, turning the unfinished cylinder into a silhouette that already seemed familiar. Landing gear units gave the growing aircraft its own wheels and allowed later work to continue at floor level. Beneath each wing, a pylon formed the structural and systems bridge, where a turbofan would eventually hang. Within the shell, wiring, pipes, ducts, controls, and sensors gradually connected distant parts into one aircraft. Floor panels, insulation, sidewalls, bins, galleys, and seats changed the hollow fuselage into a usable cabin. Paint made the outer surface look complete, though testing still stood between the aircraft and passenger service. Passenger A330s continued to reach final assembly in Toulouse, the program's long-standing industrial home. The first flying passenger version was the longer A330-300, now ready to leave the factory floor. Before flight, teams checked systems on the ground, where instruments could be watched without leaving the apron. Structures were tested against planned loads, turning calculations into measured movement and recorded evidence. Taxi trials let brakes, steering, engines, and ground handling work together, while the tires stayed on concrete. On November 2nd, 1992, the first A330-300 flight lifted away from Toulouse. The aircraft that had existed as sections and drawings was now moving through the air as one complete machine. Flight testing allowed engineers to compare predicted behavior with what instruments and pilots observed in real conditions. A test cabin could hold measurement stations instead of ordinary seats, gathering information throughout each planned maneuver. higher and farther flights explored the operating envelope gradually, with each result feeding the next test plan. Every landing returned the aircraft to the ground, where observations could become inspections, adjustments, and another flight. Certification gathered those demonstrations into a documented case that the design met the applicable requirements. The shorter A330-200 followed later, extending the passenger family without replacing the longer version. Commercial service began with Air Inter, the French airline that first placed the A330 into revenue operation. That beginning came in January 1994, a little more than a year after the first flight. One early route linked Paris-Orly and Marseille, showing the widebody at work on a comparatively short sector. For travellers, the new program arrived not as an engineering chart, but as a doorway and an assigned seat. The cabin offered the wide cross-section already associated with Airbus widebodies, arranged according to the airline's needs. Shorter journeys demonstrated that a large twin-engine aircraft did not have to spend every flight crossing an ocean. As other operators adopted the family, longer services revealed how comfortably the same basic form could change roles. New routes accumulated one by one, turning an unfamiliar aircraft into a repeated sight at distant terminals. Overnight arrivals and departures gave the aircraft a rhythm measured less by spectacle than by dependable repetition. To understand that familiar form more closely, we can now place its principal versions side by side. The family portrait includes shorter and longer passenger aircraft, renewed Neo versions, and a purpose-built freighter. The classic A330-300 is the longer of the two principal early passenger variants. The classic A330-200 uses a shorter fuselage while keeping the recognizable wide-body cross-section. Among the passenger Neo aircraft, the A330-900 carries the longer fuselage. Its shorter Neo companion is the A330-800, shaped around a different balance of capacity and range. The A330-200F is a purpose-built freighter, recognizable by details we will revisit later. These names matter because an engine, span, cabin feature, or range from one version may not belong to another. The 300 and 900 form the longer pair when we compare the main passenger fuselage lengths. The 200 and 800 form the shorter pair, each visibly trimmed behind the same broad cabin shape. Every dimension and capacity belongs to a particular variant, weight option, and airline arrangement, not a blended average. The A330-300 is approximately 63.7 meters long from nose to tail. The A330-200 is approximately 58.8 meters long, noticeably shorter in matched profile. With their noses aligned, the 300's extra fuselage length appears as a calm extension towards the tail. From above, the shared wing shape makes the different fuselage lengths especially easy to see. More fuselage length gives an airline more interior volume to divide among seats, galleys, lavatories, and other spaces. Published classic specifications generally give the shorter 200 more range than the corresponding 300. Actual range still varies with weight option, payload, weather, reserves, and the way a flight is planned. At ramp level, even the shorter version rises well above nearby equipment, windows, doors, and painted guidance lines. A doorway that feels ordinary from inside becomes a small rectangle when viewed from across the apron. Baggage tugs and service vehicles move beneath the fuselage, turning familiar airport machines into useful measures of scale. The body is essentially a long, pressure-bearing shell, rounded so loads can travel smoothly through its structure. Small windows repeat along that shell, giving the exterior a visual rhythm that follows the cabin floor. Across the classic passenger variants, the wingspan is roughly 60 meters. Broader than the fuselage is long in places. The leading and trailing edges angle backward, creating the swept planform used for efficient, high subsonic flight. Near the fuselage, the wing becomes thick and deep, meeting the center section through a carefully shaped fairing. At the far end, the classic wingtip fence rises above and below the tip in a compact form. The horizontal tail provides a smaller paired surface behind the wing, ready to help control pitch. The vertical tail carries the rudder, which helps control movement of the nose from side to side. In flight, the wing may bend visibly, a planned flexibility, rather than a failure to remain rigid. Much of the aircraft's fuel rests inside tanks formed within the wings, close to the structure carrying lift. Additional fuel capacity lies around the center wing area, where the left and right wings meet the fuselage. Along the leading edge, slats wait flush with the wing until lower speed flight calls them forward. Along the trailing edge, flaps and roll control surfaces divide the wing into several carefully coordinated moving regions. Following that long span from root to tip prepares us to watch the air itself move around it. Beneath the aircraft are two main landing gear assemblies, one placed under each side near the wing. Each main unit carries 4 wheels, arranged as 2 pairs on a short bogey beam. At the front, the nose landing gear carries 2 wheels and supports the aircraft's forward end. Struts hold the wheels below the fuselage and absorb changing loads as the aircraft moves on the ground. After takeoff, the landing gear retracts into shaped bays so the exterior can become smoother for flight. On landing, those multiple tires share contact with the runway as the aircraft's weight settles back onto them. During taxi, the nose wheels follow painted lines that guide the long fuselage toward a stand or runway. Dimensions also shape airport planning, from stand clearances to the space kept around wings, tails, and service roads. A cross-section lets us leave the apron and look directly through the round fuselage wall. At its broadest interior section, the cabin is about 5.26 meters wide, just under 5.3. That published cabin measurement belongs inside the finished space, not across the aircraft's outermost surface. Between outside and inside sit structure, insulation, systems, and lining, each taking a little of the circular shell. A nearly level cabin floor crosses the lower part of the circle, leaving useful volume beneath it. 2 aisles divide the upper space and give crews and passengers more than one path through the cabin. Storage bins occupy the upper curve, using space that would otherwise sit above seated passengers. Sidewall panels soften the structural shape, framing each window and hiding much of the aircraft's working interior. The aisles create long, visible paths, interrupted occasionally where galleys, lavatories, doors, or cabin classes change. An airline decides how to divide this volume, so no single floor plan represents every A330. Cabin classes can change the number of seats across, their spacing, and the rooms built around them. Seat spacing changes capacity as surely as fuselage length, even when the exterior aircraft remains exactly the same. Circular frames and floor beams share the work of supporting the shell, cabin, and spaces below. Beneath the seats, the lower hold continues through much of the fuselage as a separate working level. The most familiar economy plan places 2 seats by one wall, 4 centrally, and 2 by the other wall. Spoken naturally, it is a 2-4-2 arrangement, adding up to 8 seats across. Airbus promotes 18-inch economy seats when the A330 is arranged 8 abreast in this way. In the standard pattern, no passenger sits more than 1 seat away from an aisle. Each window side pair contains 1 window seat and 1 aisle seat, a simple little compartment of 2. The central group of 4 is bordered by both aisles, giving its outer places direct aisle access. 2 aisles also shape cabin service, boarding flow, and the routes used by carts and crew. Some airlines choose denser seating, while others devote more floor area to each traveller or cabin class. Premium sections often use fewer seats across, showing how strongly furniture can alter the experience of the same width. Galleys, lavatories, closets, crew spaces, and partitions further change how much of the fuselage becomes seating. Many passenger layouts fall broadly around 250 to 300 seats, depending on variant and configuration. Below the window line, a cargo door opens into the part of the aircraft passengers seldom see. The A330's lower hold can accept standard LD 3 containers side by side. Their sloping lower corners follow the fuselage curve, turning an awkward rounded space into regular cargo positions. Some containers hold checked bags, gathered out of sight, while passengers settle into the cabin above. Other positions can carry revenue cargo, letting a passenger flight move more than travellers and suitcases. Rollers help each container move into place, and floor locks secure it for the journey. Once the doors close, cabin and hold travel as 2 organised levels within one pressure-shaped body. Returning outside, the classic aircraft ends its wing with the small fence we noticed at the gate. The Neo uses a redesigned wingtip device, a clear visual clue that the familiar wing has evolved. Placed together, the Neo's wider wing and different tip treatment distinguish it without changing the basic family resemblance. One profile becomes the other, almost gently, preserving the fuselage while changing engines and aerodynamic details. At 20 minutes, our view rests on the wing, ready to follow the patient work of moving air. The wing does not hold the aircraft up by resting on air as though it were a shelf. Instead, its shape and angle create aerodynamic forces around a moving flow. The wing turns some of that flow, while a changing pressure pattern develops across its surfaces. Together, those effects produce lift. Imagine following one small region of air as the A330 advances. The flow divides around the wing, speeds and pressures change, and the air leaves with a different direction from the one in which it arrived. The reaction to that turning helps support the aircraft's immense but smoothly carried weight. The A330 uses a supercritical airfoil, shaped for efficient flight near the upper end of the subsonic range. Its contour manages the pressure changes that appear as the aircraft moves quickly through thinner, high-altitude air. The name may sound dramatic, but the underlying idea is simply careful shaping for cruise. From above, the backward sweep becomes unmistakable. The wing roots begin near the middle of the fuselage, but the tips sit much farther behind. This geometry suits efficient high subsonic travel and gives the aircraft the poised outline we recognized at the gate, even when it is standing completely still. A typical cruise speed is around Mach 0.82, though weather, weight, routing, and operating decisions can change the precise value. Mach 0.82 is still below the speed of sound. From inside the cabin, this rapid motion can feel almost motionless against a distant horizon. Cruise is only one part of a flight, so the wing can change shape when the aircraft slows. Slats move forward from the leading edge, opening and reshaping the front of the wing. Their extension helps the wing produce the lift needed at the lower speeds used around takeoff and landing. Flaps perform related work along the trailing edge. When extended for takeoff or landing, they increase the wing's effective curvature and area. The clean cruise shape becomes a more elaborate low-speed shape, with visible gaps and surfaces arranged to keep useful airflow attached as speed decreases. Ailerons help control roll, the motion that raises one wing while lowering the other. Their movements can be small, especially during gentle corrections in cruise. One side changes lift relative to the other, and the broad aircraft responds with a gradual bank rather than an abrupt turn. Spoilers are panels on the upper wing that rise into the airflow. Selected panels can assist roll, help manage descent, or reduce lift when the aircraft is firmly on the runway. Their name describes what they do aerodynamically. They disturb part of the smooth lifting flow in a controlled and useful way. After touchdown, a broader spoiler deployment helps the aircraft settle onto its landing gear. Reducing wing lift places more of the aircraft's weight on the wheels, allowing the wheel brakes to work effectively. We will return to that sequence near dawn, when our quiet route reaches the runway. The wing is not working alone. At the rear, elevators on the horizontal tail help control pitch, the movement that raises or lowers the nose. Their carefully managed deflections balance forces across the aircraft, keeping the desired attitude as speed, weight, and flight condition gradually change. The rudder sits on the vertical tail and helps control yaw, the side-to-side direction of the nose. Pilots and flight control systems use it when conditions require. Seen from outside, the movement is modest, but its position far behind the center of the aircraft gives it useful leverage. Each surface has a distinct job, yet a real maneuver may involve several of them together. A bank changes lift direction, the tail helps manage attitude, and the engines maintain or alter energy. The result is not one isolated mechanism, but a coordinated conversation between air, structure, controls, computers, and crew. The wing also bends. From a window, its tip may rise and fall slightly as the aircraft crosses changing currents. That visible flex is an intended property of the structure, allowing loads to be carried without demanding absolute rigidity. Movement within designed limits is part of the wing's patient work. Inside the outer skin, spars and ribs give the wing its form and carry forces toward the center section. The details are hidden during an ordinary flight, but their effect is visible in the smooth surface outside. A thin-looking shape becomes a deep, organized structure near the fuselage. Those internal spaces also hold fuel. Wing tanks place much of the supply within the lifting structure itself, rather than in a separate container somewhere in the fuselage. As fuel is used, the aircraft's mass slowly changes, even while the cabin scene and the distant stars may appear unchanged. Passenger A330s also have fuel capacity in the center wing area. This central region lies where the wings join the fuselage, close to the strongest crossing of the airframe. Its capacity belongs to a broader fuel system whose details can vary with variant and configuration. Fuel does not simply disappear from whichever tank happens to be nearest an engine. management systems control its order of use and help maintain an appropriate balance. Pumps, valves, sensors, and automatic logic make the supply available while keeping the changing distribution of mass within planned limits. With its surfaces clean and fuel moving quietly through hidden paths, the wing can continue for hours above cloud. The air is always flowing, and the structure is always carrying load, yet the view remains composed. That contrast is one of the gentlest facts about high-altitude flight. Near the wing root, our attention reaches the pylon and the rounded nacelle below it. The wing provides lift, but the aircraft also needs a steady source of thrust, electrical power, and pressurized air. For those services, we can follow the airflow into one of the two turbofans. Classic A330 variants have been offered with three principal engine families. Airlines could receive General Electric CF6 engines, Pratt & Whitney PW4000 engines, or Rolls-Royce Trent 700 engines. Each family has its own details, but all three belong to the high bypass turbofan type. The General Electric option is from the CF6 family. Its nacelle gives the wing a broad, rounded form underneath, with a large inlet leading toward the fan. From a passenger window, much of the complex machinery remains hidden behind smooth panels and the dark circle of the intake. Another classic choice came from Pratt & Whitney's PW4000 family. It performs the same broad task of turning fuel and airflow into thrust while using its own internal design. Engine selection is therefore a variant and operator detail, not a feature shared identically by every classic aircraft. The third family is the Rolls-Royce Trent 700. It too has powered classic A330s across medium and long services. Later, the Neo will bring a different Rolls-Royce engine, so it is useful to keep the Trent 700 and Trent 7000 clearly separate. In a high bypass turbofan, a large share of the incoming air travels around the engine core. The fan gives this bypass flow momentum, and that moving mass of air contributes much of the thrust. Only a smaller portion enters the hotter, more compact machinery along the centerline. Begin at the inlet, where the aircraft's forward motion and the turning fan draw air into the nacelle. The flow separates into two paths. One passes around the core through the bypass duct, while the other moves inward toward compressor stages, combustion, and turbines. The fan is the first great rotating structure encountered by the air. Its blades sweep a broad circle, accelerating a substantial flow rearward. Although the actual rotation is rapid, a slowed diagram lets us see the simple pattern. Air enters from ahead and receives energy from the turning blades. Air entering the core passes through compressor stages. Rows of rotating and stationary blades progressively raise its pressure before combustion. The passage narrows and the components become smaller, so the broad, cool stream at the inlet is prepared for a much more concentrated release of energy. Inside the combustor, fuel adds energy to the compressed airflow. This is the warmest part of our mechanical journey, but it occupies a contained region deep within the engine. The expanding hot gases continue rearward, carrying the energy needed by the turbine stages that follow. Turbine blades take part of that energy from the hot flow. Through concentric shafts, the turbines drive the compressor and fan toward the front. The engine therefore sustains a continuous cycle. Compression supports combustion, combustion energizes the turbines, and the turbines keep the rotating machinery moving. Both the bypass stream and the core exhaust leave toward the rear, producing a forward reaction on the aircraft. Thrust is the quiet result of a great deal of organized airflow. At cruise, engine control settles this process into the level needed for speed, altitude, weather, and weight. The engine cannot simply hang from the wing by its outer cover. The pylon carries structural loads into the wing and also provides routes for electrical, fuel, pneumatic, and control connections. Its fairings smooth the airflow around a region that is both a strong attachment and a busy systems bridge. A full authority digital engine control manages engine operation within commanded limits. It interprets requests from the flight deck and coordinates fuel flow and other variables while monitoring the engine. The pilot's command thrust and the control system handles many fine adjustments needed to deliver that command consistently. Each running engine can also drive a generator. In flight, engine-driven generators supply electrical power for displays, pumps, lighting, computers, galleys, and many other users. The turbofan is therefore not only pushing the aircraft forward, it is also turning part of the machinery that keeps the aircraft electrically alive. Compressed air from the propulsion system supports pneumatic services, including cabin conditioning on the A330. A controlled portion can be taken from the compressor, routed through ducts, and sent toward the systems that prepare air for the occupied fuselage. It is managed carefully because engine and cabin needs both change. Air conditioning packs cool and condition the compressed supply before it reaches the cabin distribution system. Heat exchangers, valves, and control logic turn very warm pressurized air into something suitable for breathing and temperature control. The soft airflow at a passenger vent begins with this largely unseen chain beneath the floor. The nacelle also contains acoustic treatment. Carefully shaped liner surfaces are designed to reduce portions of engine noise by interacting with sound inside the inlet and duct. They cannot remove every frequency, but they help shape the sound that travels outward, and the sound eventually perceived within the cabin. What passengers hear is a blend rather than a single source. Engines contribute, but so do fast exterior airflow, ventilation equipment, pumps, moving air, and the airframe itself. Seat location and aircraft configuration alter the balance, which is why the familiar cabin hum can change from row to row. After landing, reverse thrust can supplement the wheel brakes. Parts of the nacelle redirect airflow so that engine thrust helps oppose forward motion. It is an additional tool rather than the principal controlled braking force, and its brief change in sound belongs to the transition from flight back to the ground. Thrust, electricity, and conditioned air all reach beyond the nacelle. Their condition must be commanded, displayed, and monitored somewhere, so our view follows the wiring and ducts inward. Ahead of the wing is the dim room where two pilots organize the aircraft, route, weather, and changing phases of flight. The A330 flight deck is designed for two pilots. One seat is on the left and one on the right, with shared displays and controls arranged around them. The room is compact compared with the cabin behind it, yet it gathers information from throughout the aircraft and far along the route. Instead of central control columns, A330 pilots use side stick controllers. Each small stick sits beside its pilot, leaving the space directly ahead relatively open. A movement of the hand represents a requested change in pitch or roll, which the electronic flight control system then receives and processes. This is part of the aircraft's fly-by-wire design. Pilot inputs travel as electrical signals to flight control computers, rather than moving the control surfaces through a continuous mechanical linkage from the cockpit. Computers interpret those inputs and command actuators that move the relevant surfaces on the wing and tail. Electronic transmission allows control laws and multiple computer channels to take part in the process. The precise architecture is complex, but the basic chain remains understandable. A pilot makes an input, computers process it, actuators respond, and the aircraft's motion returns through instruments and physical sensation for continued supervision. Across the main panel, electronic screens create a glass cockpit arrangement. They show attitude, speed, altitude, navigation, engine indications, and system information in organized regions. Brightness can be reduced for night work, allowing important colors and symbols to remain clear without flooding the cockpit with light. The electronic centralized aircraft monitor presents information about aircraft systems and alerts. Its displays allow the crew to view the condition of engines, electricity, hydraulics, fuel, air, doors, and other systems. When attention is needed, the system helps organize what has changed and which procedure applies. The flight management system stores and computes route and performance information. Before and during flight, the crew enters, checks, and updates relevant data. The system can build a connected path through waypoints and help calculate how speed, altitude, distance, weight, and fuel relate along that path. On a navigation display, a route becomes a line joining named points and coordinates. The aircraft does not follow a glowing mark painted in the sky. It computes position, compares that position with the planned path, and presents the relationship so pilots can monitor where the flight is going. The autopilot follows modes selected or managed through the flight guidance system. Depending on the active mode, it can maintain or change headings, tracks, altitudes, vertical paths, and speeds. These actions remain part of a crew-directed plan, with the pilots choosing modes, checking outcomes, and changing the guidance when needed. Autothrust can manage engine thrust according to the active mode. It may hold a commanded speed or provide thrust appropriate to another flight phase. The system coordinates the engines precisely, but its purpose is not to make the crew unnecessary. It is one more supervised tool within the flight deck. Pilots remain responsible for selecting, supervising, and intervening in automated systems. They compare displays, listen to communications, review weather, and anticipate what comes next. Automation can carry out steady control tasks, while the crew maintains the larger understanding of aircraft state, route, airspace, and operational intent. Outside the cockpit, pitot and static sensors sample pressure. Their data is used to calculate airspeed and pressure altitude, two basic measurements for controlled flight. Small openings on the forward aircraft therefore feed information that appears as stable numbers and moving scales directly in front of the pilots. Inertial reference systems track the aircraft's motion without depending continuously on ground beacons. Internal sensors measure changes in movement and orientation, allowing position to be carried forward between outside updates. This quiet form of dead reckoning is especially useful when the nearest land and radio sites are far beyond the horizon. Satellite and radio navigation inputs can update the aircraft's computed position. The flight management system blends available information rather than relying on one permanent external source. As the route crosses different regions, The mixture of usable aids may change, but the crew continues to see one coherent navigational picture. Onboard weather radar sends energy ahead and interprets reflections from precipitation. Its display helps the crew see patterns that may affect the route, particularly within rain-bearing weather. Pilots can use that information alongside forecasts, reports, and visual cues to choose an appropriate path around significant returns. Weather radar has limits. It does not directly reveal every form of clear air turbulence because air without suitable moisture. Returns may not produce the same visible pattern. A quiet-looking screen is therefore one source of information, not a promise that every invisible movement ahead has been mapped. During the lower part of flight, radar altimeters measure height above the terrain beneath the aircraft. This differs from pressure altitude, which is derived from atmospheric pressure. Near the runway, the direct height information supports displays, call-outs, and systems whose work becomes most relevant close to the ground. Cockpit lighting is dimmable for night operation, so panels can remain readable while the outside view stays visible. Airbus also uses cockpit commonality across related types, reducing some differences pilots encounter as they move through the family. Familiar layouts and philosophies can make a new variant less unfamiliar. Behind the pilots, the same aircraft systems become a lived environment of air, light, temperature, sound, and space. The cockpit monitors that environment, but the cabin is where hundreds of small physical details are felt directly. We can now move through the door and examine the quiet room within the pressure shell. Outside the aircraft, the air at cruise altitude is cold and thin. Inside, passengers sit in a deliberately managed environment where pressure, temperature, and airflow are kept within useful ranges. The difference exists because the fuselage is more than an outer shape. It is also the boundary of a pressurized cabin. The pressure shell surrounds the occupied spaces and carries the difference between cabin pressure and the air outside. Doors, windows, and structural joints all form part of that boundary. Its rounded cross-section distributes loads efficiently, which is one reason the circular form has followed us through every view of the aircraft. Cabin altitude is far lower than the aircraft's physical cruising altitude. The phrase cabin altitude describes the pressure inside by comparing it with a corresponding height in the standard atmosphere. It does not mean the cabin is physically at that lower level. It is a convenient way to describe pressure. For the A330neo, reported cruise cabin altitude figures sit broadly in the 7,000 to 8,000 foot range. The exact value depends on model, aircraft altitude, and the pressurization schedule, so the range is more useful here than one universal number. It describes an operating environment, not a promise of comfort or sleep. Cabin pressure changes throughout a flight. During climb, the system follows a planned schedule rather than allowing the interior to copy the rapid pressure decrease outside. During descent, that process gradually reverses. The aim is a controlled cabin environment that reaches the destination pressure as the aircraft returns to the ground. Some of the air entering the cabin begins outside and passes through the propulsion system, where it is compressed. It is far too warm and at the wrong condition to enter directly. Ducts and control valves carry a managed supply toward the air conditioning equipment beneath the aircraft's central fuselage. The packs cool and condition the compressed supply. From there, distribution ducts carry prepared air into the cockpit and cabin. What reaches a ceiling outlet has already passed through several stages of compression, temperature change, regulation, and mixing, even though the final sensation may be only a faint stream above a seat. Cabin ventilation combines outside air with recirculated air. Drawing some cabin air back through the system allows airflow to continue efficiently, while a fresh outside portion is introduced and an equivalent amount leaves the pressure vessel. The mixture is distributed repeatedly, so the cabin is not a sealed room with motionless air. High-efficiency particulate filters are used in the recirculation system, subject to the equipment installed on the particular aircraft. These filters remove very small airborne particles from the recirculated portion before it returns to occupied spaces. Filtration and outside air replacement perform related but different roles within the overall ventilation process. Long-haul cabin air is usually drier than ordinary indoor air at sea level. The low moisture content of the outside atmosphere and the way cabin air is managed both contribute. Some people notice dryness more than others, which is one reason individual experiences of the same flight can differ substantially. Temperature control zones allow different parts of the aircraft to be regulated. A sensor reading and a selected temperature help the system adjust the air delivered to a zone. The cabin is still one connected volume, but separate control areas can respond to differing heat loads, occupancy, equipment, and crew selections. Behind the visible sidewall, portions of the fuselage are lined with thermal and acoustic insulation. The material helps moderate heat transfer and reduces parts of the noise traveling through the shell. Passengers normally see only the finished panel, while the layered blankets and structure remain hidden just a short distance away. An aircraft window is not one thin sheet separating a seat from the upper atmosphere. It uses multiple panes with distinct structural and protective roles. Their layered construction is why reflections can appear at slightly different depths, especially at night when cabin lights hover faintly over the dark wing outside. The seat itself is chosen by the airline, not fixed forever by the aircraft family. Width, spacing, recline, cushioning, head support, and cabin class all affect the space a passenger feels. 2. A330s with matching exteriors may therefore contain interiors that look and feel noticeably different. What remains common is the broad twin-aisle geometry. The cabin width offers room for several possible seat patterns, while the two pathways organize movement along the aircraft. Yet even this shared shape does not guarantee a particular experience, because furnishing choices determine how the available volume is actually used. The A330neo's airspace cabin includes full-color, light-emitting diode, ambient lighting capability. Airlines can select programs that alter color and intensity across a flight. The capability belongs to the cabin system, while the particular sequence seen by passengers depends on the operator and the choices made for that aircraft. Airbus also offers larger overhead storage in the A330neo airspace interior than in earlier standard A330 cabins. More bin volume can change how belongings are distributed above the seats. It is an interior feature of the newer cabin offering, not a detail that should be projected backward onto every classic aircraft. Airbus has promoted quieter lavatory features as part of the airspace cabin. That is a manufacturer description of a designed feature, not a claim that every sound disappears. Pumps, doors, ventilation, water systems, and passengers still create an ordinary working environment within a small enclosed compartment. Not every A330 contains the same seats, bins, lighting program, lavatories, or entertainment equipment. Cabins can be refurbished during an aircraft's life, making variation possible, even within one airline's fleet. The family supplies a structural volume and system options, while operators decide how much of that potential appears inside. Light can influence the body's sense of time. Bright light at night can suppress melatonin and alter circadian timing, which is why a dim environment may feel gentler before rest. This is a general effect of light exposure, not evidence that any aircraft cabin guarantees sleep or treats a sleep problem. A steady broadband sound can mask some intermittent noises by reducing the contrast between a brief sound and the background. The cabin's blend of airflow and machinery may sometimes have that effect. Other listeners may find the same sound noticeable, and its character changes with seat position, aircraft, and phase of flight. Responses to light, sound, pressure, dryness, temperature, and seating are individual. A detail one traveller barely notices may remain distinct to another. The aircraft creates a managed environment, but it cannot promise the same sensation to everyone. Beyond the window, our attention can now widen from the cabin to the ocean route itself. A long route is first a line across a curved earth. The shortest surface path between distant points is generally a great circle route, though real flight planning must also consider winds, weather, airspace, and available airports. The final track is therefore a practical path, not merely the neatest geometric arc. When that path is placed on many flat maps, it appears curved. Nothing strange has happened to the route. The map projection has changed how the globe is represented. A line that looks like a bow across an ocean may be close to the natural shortest path over the planet's surface. For qualifying twin-engine flights far from suitable diversion airports, a regulatory framework called extended operations applies. Its familiar aviation name is pronounced ETOPS. The framework does not rest on one slogan or one feature. It combines aircraft design approval, engine pairing, airline procedures, maintenance, dispatch planning, and crew operation. An extended operations route must remain within the approved diversion time of a suitable airport under the applicable planning conditions. On a map, this can be shown with overlapping reach around potential airports. The exact route and approved time depend on the operation being planned, rather than one permanent circle for every flight. Suitable means more than placing a runway near the line. Dispatchers consider weather, runway capability, airport status, available services, operating hours, and other requirements. An airport that exists geographically may not be suitable for a particular flight at a particular time, so the planning picture changes as conditions change. Type approval applies to a defined aircraft and engine combination. That detail matters because the same airframe family can use different engine families, as we saw earlier. Each approved combination is considered on its own evidence, rather than granting every possible aircraft and engine arrangement the same status automatically. The airline also needs the relevant operational and maintenance approval. Procedures, training, reliability programs, dispatch practices, and continuing maintenance all form part of the permission to conduct these flights. A capable aircraft alone is not the whole system. The operator must show that it can plan and support the operation consistently. After the family entered service, A330 aircraft and engine combinations gained progressively longer extended operations approvals. Those developments came through accumulated evidence, certification work, and operational experience. The route possibilities widened over time, but each approval still retained its conditions and did not erase the need for careful flight-by-flight planning. Certification includes demonstrated performance with one engine inoperative. This does not mean a flight plan depends casually on losing an engine. It means the aircraft and engine combination must satisfy defined performance and systems requirements for the diversion case, while the broader operation continues to rely on planning, redundancy, crew action, and maintenance. Long-range operation depends on redundancy in critical systems. In the electrical network, multiple sources and distribution paths help preserve essential functions when one source is unavailable. The exact architecture contains many details, but the calming principle is straightforward. Important services are not casually entrusted to one unshared path. Hydraulic power is similarly divided across systems and users. Different flight control surfaces can receive power through planned arrangements, reducing dependence on a single circuit. Redundancy does not make faults impossible. It gives the aircraft defined ways to preserve necessary functions, while a crew follows the appropriate procedures. Navigation and communication also use more than one means. Inertial systems continue tracking motion, outside sources can update position, and different communication links become available in different regions. The route across open water is therefore supported by overlapping tools, rather than one uninterrupted connection to a single point on land. Dispatch fuel planning includes more than the amount expected for the direct route. The plan accounts for applicable reserves and other required portions, including circumstances in which the flight cannot simply continue exactly as forecast. The details depend on regulations and operation, but the result is deliberately more layered than distance divided by fuel flow. Wind forecasts can change both flight time and fuel requirements. A strong flow from behind may shorten one journey, while a headwind may lengthen the return. Routes can shift to use more favorable air or avoid less favorable regions, so the most useful path may differ from the pure geometric shortest line. Weather can also alter the selected route and the choice of alternates. Forecasts are reviewed before departure, then observations and updates continue during flight. A line drawn earlier is not treated as untouchable. It can be amended as conditions, air traffic constraints, and the practical options ahead become clearer. The suitability of a diversion airport is therefore time-sensitive. A runway may be long enough, yet weather or availability can change the decision. Dispatchers and crews work with current information, looking not only at where an airport sits, but at whether it can serve the planned aircraft under the relevant conditions. Across oceanic airspace, flights navigate through defined coordinates and waypoints. These points organize routes where ordinary ground references are absent. The flight management system joins them into a computed path, and crews verify clearances and progress as the aircraft moves from one invisible coordinate to the next. Inertial navigation allows position tracking between external updates. Because it measures the aircraft's own motion, it does not need a nearby ground beacon at every moment. Satellite and radio inputs can refine the computed position when available, creating a quiet partnership between self-contained sensing and information received from outside. Where ordinary line-of-sight radio coverage is unavailable, long-range aircraft may use high-frequency radio or satellite links. Their use depends on equipment, region, and procedure. The crew may be far from a visible coast, but the flight remains part of an organized communication and traffic management system extending beyond the horizon. From the window, none of these layers looks busy. There is only the wing, 2 engines, a dark surface far below, and perhaps a thin band of moonlight. The route's complexity lives mostly in approvals, forecasts, systems, procedures, and displays, allowing the exterior scene to remain remarkably simple. Long-range twin-engine economics helped make some lower-demand city pairs practical, without requiring a larger 4-engine aircraft. A broad cabin could connect places with enough demand for a widebody, but not necessarily enough for the largest type. The A330 found useful work in that middle ground between capacity and reach. As our single ocean line reaches land, it joins thousands of other paths flown across the family's operating life. One carefully planned route becomes part of a much wider pattern of repeated departures and arrivals. We can pull back now and see how broadly that practical twin-engine shape has spread. Airlines have operated the A330 family on every inhabited continent. The aircraft has crossed hot, cold, humid, dry, coastal, inland, high latitude, and tropical regions. Its basic outline remains recognizable across them all, even as liveries, cabin layouts, engines, and daily assignments change. The map becomes more tangible when it is seen as a sequence of stands and runways. An A330 can wait beneath winter cloud at one airport and later appear under warm coastal light elsewhere. The geography changes, but the routines of loading, checking, fueling, boarding, and departure remain closely related. Every inhabited continent does not mean every country or every airport. It means operators across the world's populated continental regions have found roles for the family. The statement describes breadth, while leaving room for the routes and fleets that change over time as airlines adjust their networks. At major hubs, A330s have carried passengers into banks of connecting flights. A widebody can gather many journeys into one trunk service, then distribute travellers onward through the network. The aircraft becomes one moving room within a much larger timetable of gates, crews, bags, and onward connections. The family has also served lower demand long-distance routes, where a still larger aircraft might provide more capacity than the market requires. This flexibility is part of its workhorse character. The same broad cabin can support a busy hub route on one assignment and a thinner city pair on another. Production began in the 1990s and continued into the 2020s, spanning classic passenger aircraft, the factory freighter, specialist relatives, and the neo renewal. Few manufactured objects remain current across so many changes in cabins, engines, communications, passenger expectations, and airline networks without evolving along the way. In 2013, Airbus delivered the 1000th A330 family aircraft to Cathay Pacific. The milestone represented many individual airframes, rather than one abstract total. Each had its own assembly sequence, delivery flight, registration, cabin, maintenance history, and repeated place in an airline's timetable. By the end of May 2026, Airbus said the A330 family had won more than 1,950 orders. The date matters because order books change. This is a snapshot tied to the manufacturer's reconciliation, not a number that should be repeated forever. without checking it again. The same Airbus statement gave 133 customers worldwide. A customer count is not identical to the number of current operators, because orders, leasing, ownership changes, deliveries, and fleet retirements create different categories. It is best understood as another dated measure of the program's broad commercial reach. Order and delivery totals are living records. Contracts can be added, cancelled, or converted, and completed aircraft move from the order book into the delivered fleet. A precise number therefore belongs with an as-of date. The slower truth is that the family has accumulated demand across several decades. Passenger A330s carry revenue cargo in their lower holds as well as baggage. The containers beneath the floor can hold shipments moving on the same route as the people above. A passenger flight is therefore also part of a freight network, using volume that the wide-body cross-section makes available. Baggage follows passengers, while revenue cargo may connect businesses, postal systems, or other transport chains. Both must be weighed, documented, loaded, and secured in their assigned positions. What appears from the cabin as a quiet wait at the gate includes an organized exchange occurring through doors below the windows. Aircraft leasing can allow one A330 to serve more than one airline during its operating life. A change of operator may bring new paint, seats, records, and routes, while the underlying airframe continues. The aircraft's biography can therefore be longer and more geographically varied than one airline name suggests. By wingspan, the A330 falls within International Civil Aviation Organization Code E. Both the classic span and the approximately 64-meter neo span remain in that category. The code helps airports plan clearances and facilities around aircraft whose dimensions sit within the same broad reference group. A Code E stand accounts for the space needed around an aircraft in the A330's general size category. Wing clearances, taxi lanes, pavement, bridges, and service access all influence the fit. Airport compatibility is not one doorway measurement. It is a three-dimensional arrangement of aircraft and infrastructure. During a routine turnaround, several tasks may proceed in parallel. Catering reaches one door, baggage and cargo move below. Fuel is supplied under controlled procedures. Water and waste services connect. Cleaners work inside, crews inspect the aircraft, and passengers eventually board. The quiet stand becomes a carefully divided workplace. Maintenance continues at many scales, from a walk-around inspection to scheduled work inside systems and structures. Records connect what technicians find with what has already been done and what will be required later. Repetition is useful here. The aircraft remains available because small checks and planned tasks recur throughout its life. At one end of the story, new aircraft leave Toulouse. Elsewhere, earlier airframes continue flying, change operators, receive cabin updates, or enter conversion programs. Production and continued service overlap, so the family exists not as one age group, but as many individual machines at different points in their working lives. The workhorse reputation grows from that repetition. Range, cabin volume, cargo space, and airport compatibility create many possible assignments, but usefulness is proven one completed schedule at a time. There is no single dramatic moment when an aircraft becomes familiar. Familiarity accumulates through ordinary work seen again and again. Some branches of the family carry that usefulness in unexpected directions. Rows of seats can give way to pallets, fuel transfer equipment, medical modules, or an enormous upper fuselage for aircraft parts. The shapes change, but the familiar wing and lower fuselage remain, ready to lead us into the A330's specialist relatives. The A330-200F is the family's factory-built cargo aircraft. Its basic proportions recall the shorter passenger 200, but the working interior and several exterior details reveal a different purpose. Instead of arranging the main deck around rows of travelers, the freighter is designed around pallets, containers, loaders, and freight handling. The factory freighter entered commercial service in 2010. By then, the passenger family had already been flying for many years, giving the new version a mature airframe foundation. Its arrival added a main deck cargo role, while retaining the recognizable twin-engine wing, forward profile, and broad lower fuselage of the A330. A large main deck cargo door opens high on the forward side of the fuselage. Its rectangular opening is sized for loads that could never pass through an ordinary passenger doorway. When the door is closed, its outline remains visible as a broad seam above the distinctive lower nose fairing. That fairing beneath the nose is one of the easiest ways to recognize the 200F. It is associated with a modified nose landing gear installation. The change is not decorative. It helps alter the freighter's ground attitude, so the long main cargo deck can sit more nearly level during loading. A level main deck matters because heavy pallets and containers must move predictably through the door and along the floor. The modified nose gear geometry reduces the natural nose-down slope that would otherwise complicate handling. A small-looking change beneath the forward fuselage therefore improves the usefulness of a much larger space above it. Inside, the passenger windows give way to a long working deck with restraint points, rollers, guides, and room for standardized loads. The cargo floor must carry concentrated weight and keep each unit fixed in its assigned position. What was once imagined as rows of seats becomes a measured grid for freight. Pallets can carry irregular packages beneath shaped covers, while containers enclose other loads within rigid shells. Each unit is built up, weighed, documented, and assigned before entering the aircraft. Once aboard, floor locks and restraints prevent movement, turning many separate shipments into one carefully distributed aircraft load. A high loader raises freight to the main deck door, bringing its platform level with the aircraft floor. Units then move across rollers, rather than being lifted by hand through the interior. The process joins warehouse, vehicle, loader, aircraft, and destination handling into one continuous logistics chain. Factory construction is not the only route to an A330 freighter. Passenger 200 and 300 airframes can enter approved passenger-to-freighter conversion programs. The work gives an existing aircraft a new main deck role, extending usefulness beyond the cabin arrangement for which that individual airframe was first delivered. Conversion is a substantial engineering project, not simply the removal of seats. The airframe receives the structural changes, cargo door, floor provisions, systems work, and certification needed for freight operation. The resulting aircraft remains traceable to its passenger history, while gaining a new interior designed around load positions instead of aisles. Another specialist branch is the A330 multi-role tanker transport, derived from the A330-200. Its familiar fuselage can support transport duties, while specialized equipment allows fuel transfer in flight. The engineering interest lies in how existing volume, fuel capacity, and long-range capability are reorganized for several practical roles. Some multi-role tanker transport configurations can use a refueling boom. The rigid, controllable tube extends from the aircraft and transfers fuel to a compatible receiver. From an engineering perspective, the task is one of close relative position, fluid transfer, structural control, communication, and carefully matched equipment. Configurations can also use hose and drogue equipment. A flexible hose trails a basket-shaped drogue that stabilizes the coupling point in the airflow. Different receivers and operators require different arrangements, so the multi-role tanker transport can be fitted around the transfer method specified for its intended service. The aircraft can combine air-to-air refueling with passenger or cargo transport roles. Cabin and hold arrangements can carry people, equipment, or freight according to configuration. The word multi-role is therefore literal. The airframe is useful not only as a flying fuel transfer platform, but also as a wide-body transport. An aeromedical evacuation configuration can place medical modules, stretchers, support equipment, and attendants within the wide cabin. The purpose is transport and care rather than ordinary airline seating. The broad fuselage and long deck provide room to organize equipment while preserving access around patients during a journey. Much of the transferable fuel can be carried within the airframe's existing fuel system. Using wing and central fuel capacity means the main passenger or cargo deck does not have to be filled with separate transfer tanks for the basic role. The same hidden volumes that supported long passenger flights become part of a specialist fuel mission. The most visually unusual relative is the Beluga XL. Beneath its enormous upper shell are structures based on the A330 family, including a familiar lower fuselage and wing foundation. The result preserves enough family geometry to be recognizable, even though the upper body swells far beyond a passenger cabin's outline. Airbus uses the Beluga XL to carry large aircraft components between production sites. Wings and fuselage sections that would be awkward to move by other means can enter its oversized hold. The first Beluga XL entered Airbus service in 2020, giving the A330 family tree its broadest and most softly improbable silhouette. After the freighter, tanker transport, and Beluga, the passenger Neo looks almost restrained. Its fuselage remains closely familiar, but the engines, wingtip treatment, span, and cabin offering have changed. Airbus renewed a known airframe rather than discarding its useful cross-section, and the matched profiles make that continuity easy to see. The letters in A330neo stand for New Engine Option. The name places the central change directly in the title, but the renewal extends beyond the engines. Aerodynamic refinements, a wider span, weight options, and the airspace cabin all contribute to the newer form of the family. Airbus launched the A330neo program in 2014. The decision came more than 2 decades after the first A330 flight, showing how a long-lived design can receive a new development cycle. The program would produce 2 passenger variants based on the established shorter and longer fuselage lengths. Those variants are the A330-800 and A330-900. The 800 carries the shorter fuselage, while the 900 carries the longer one. Their names echo the earlier 200 and 300 size relationship, though the Neo aircraft belong to a distinct, updated generation. Production A330neo aircraft are powered exclusively by Rolls-Royce Trent 7000 engines. This separates them from classic A330s, which were offered with 3 engine families. The Trent 7000 is therefore a reliable identification clue when the full engine and wingtip details are visible. The underlying turbofan story remains familiar. A large fan moves a broad bypass stream, while a smaller core compresses air, adds energy through combustion, and drives turbine stages. The exact design has evolved, but the calm sequence of fan, compressor, combustor, turbine, and exhaust still gives us a useful way to understand it. At the end of the wing, the Neo replaces the classic aircraft's compact fence with a redesigned wingtip device. The outer wing has a longer, more flowing finish. This change, together with other aerodynamic refinements, makes the tip one of the clearest ways to distinguish the updated aircraft from its predecessor. The A330neo wingspan is approximately 64 meters, wider than the roughly 60-meter span of the classic passenger variants. That extra breadth changes the top view proportions while remaining within the Code E airport category. Seen from a window, the renewed wing reaches a little farther into the sky. Airbus markets the A330neo as delivering up to about 25% lower fuel burn per seat than older generation aircraft of a similar size. That is a manufacturer comparison with a stated basis, not a neutral measurement covering every route, layout, payload, or operator. The attribution and the words up to both matter. Inside, the Neo introduced Airbus's airspace cabin branding to the A330 family. Full-color ambient lighting capability, larger overhead storage, and revised interior elements form part of that offering. Airlines still choose their seats and detailed layouts, so airspace supplies a design framework rather than one identical cabin for every operator. TAP Air Portugal received the first A330-900 in 2018. The delivery brought the longer Neo variant from development into airline use. Its familiar fuselage length connected it visually with the classic 300, while the Trent 7000 engines and new wingtip treatment identified the renewed generation. Kuwait Airways received the first delivered A330-800 in 2020. This shorter Neo completed the passenger pair in airline service. It is the shorter fuselage companion to the 900, preserving the family's two-length arrangement in the updated generation. In June 2026, China Eastern announced an order for 25 A330-900 aircraft. The announcement provided one recent sign that airlines were still selecting the Neo more than 3 decades after the first A330 flight. As with all order news, the date fixes the claim to a particular moment. On June 30th, 2026, SAS announced a firm order for 18 A330-900 aircraft. Airbus used the same announcement to report the family snapshot of more than 1,950 orders from 133 customers at the end of the previous month. Those orders from the middle of 2026 show commercial activity roughly 34 years after the first A330 flight in 1992. The family had moved from paired A330 and A340 drawings to classic service, specialist branches, and the Neo. Now our long route can leave the timeline and begin its descent toward dawn. Land appears first as a change on the navigation display, then perhaps as a faint concentration of light beyond the window. The aircraft leaves cruise altitude gradually, trading height for the approach ahead. Cabin pressure follows its descent schedule, engine thrust changes, and the quiet wing prepares to change shape once more. As speed decreases, the A330 extends its high-lift devices. Slats move from the leading edge and flaps travel from the trailing edge, increasing the wing's low-speed capability. The clean cruise profile becomes layered and intricate, just as it did in our earlier diagram. But now the runway is drawing nearer. The landing gear lowers into the airflow and is locked before touchdown. Two main units carry 4 wheels each, while the 2-wheel nose gear extends beneath the forward fuselage. Their arrival changes both the aircraft's outline and its sound, preparing the flying structure to become a ground vehicle again. Ahead, runway lights form a narrowing path of perspective. The pilots supervise guidance, speed, thrust, configuration, and the changing height shown by the radar altimeters. The aircraft remains a crew-directed system, with automation available according to the selected modes, and the crew ready to intervene as required. The main wheels meet the runway first. The tires begin turning, the struts accept the returning load, and the wing still carries some lift for a brief moment. Touchdown is not the end of movement. It is a carefully managed transfer from aerodynamic support to wheels, brakes, steering, and the long surface ahead. Ground spoilers deploy to reduce wing lift. With less aerodynamic support, more of the aircraft's weight rests on the landing gear, improving the effectiveness of the wheel brakes. Panels that were smooth parts of the upper wing in cruise now stand visibly in the airflow for this short, purposeful phase. Wheel brakes provide the principal controlled braking force during a normal landing roll. They act through the main wheels as the aircraft decelerates along the runway. Brake control, anti-skid functions, and crew commands manage that work, while the wing's reduced lift helps keep useful weight on the tires. Reverse thrust can supplement the wheel brakes and reduce some of the braking demand placed upon them. It is useful assistance, but the wheels remain central to normal controlled stopping. As speed falls, reverse thrust is reduced. The spoilers eventually stow, and the aircraft prepares to leave the runway. Taxi lights reveal painted lines and pavement ahead. The nose wheels follow the center line, while the long wings pass through protected clearances. After the wide sky and ocean, the aircraft is once again moving at ground speed among signs, stands, service roads, and the low buildings of an airport waking for the day. At the stand, the auxiliary power unit can supply electrical and pneumatic power while the main engines are shut down. This smaller onboard machine supports lighting, systems, and conditioned air during parts of the ground stay. It allows the 2 large turbofans beneath the wings to become completely still. External ground power can then supply the parked aircraft without keeping the auxiliary power unit running. Ground crews place chocks around the wheels to help secure the aircraft on the stand. Cables, hoses, bridges, and service vehicles reconnect it to the airport, reversing the slow separation that occurred before departure. And so we have returned to the same quiet A330, outlined by the first light of dawn. The wing is still, the engines have stopped, and the hidden systems have settled into their ground routines. The aircraft is again a patient arrangement of windows, wheels, structure, air, and space. If the details are drifting, they can keep drifting. The gate is quiet, and the journey is complete.